All right, our last topic's in Chapter 2. Chapter 2 deals with differential calculus, meaning calculus involving derivatives. And there's really two topics left that deal with derivatives, the elasticity of demand and related rates. However, neither topic is super important. Neither one is large enough to deserve its own section, in my opinion. So what I'm going to do is I'm going to throw these together. They're not super closely related, although I'm going to try my best to kind of tie them together. But really, the only reason they're together is because I don't think they each deserve half a week in our class. So first, elasticity of demand. To understand elasticity of demand, you have to understand demand functions. We've seen demand functions already a little bit in our class, but the general idea is a demand function ties together the price of a good and the quantity of that good that's demanded. Generally speaking, when the price goes up, the demand goes down. I mean, maybe there's a few weird examples where this isn't the case, like, I don't know, some sort of designer sneaker or something. You charge more and people actually want more of them. But generally speaking, for a given good, if you raise the price, people are going to want less of them. The demand curve is downward sloping. So imagine you're selling some product, and if you charge $50 for this product, you sell 10,000 units of this product. But if you raise your price a little bit, instead of $50, you charge, I don't know, $60, then demand is going to absolutely plummet. Instead of 10,000 units being sold, you only sell half as many, 5,000. These 2 points would fall on our demand curve, and if our demand curve was linear, I could connect these two dots with a straight line and get a demand curve that looks something like this. Maybe I'll call this, I don't know, product E to keep it really generic. Contrast that with some other product that if you charge $50 for, you'll also sell 10,000 units. However, in this case, if you raise your prices a little bit, raise them up to $60, the demand doesn't really change a whole lot. People still want to buy them. Maybe you sell, I don't know, 9,500 units. Again, assuming our demand is linear, we can connect these dots with a straight line and we get a demand curve that looks something like this. Keeping things super general, maybe I'll call this product I. Either way, our demand curve has a negative slope. When we go to the right, we go down. It's just a matter of how much we go down. For the blue line, we go down a lot when we go to the right. For the red line, we don't go down very much when we go to the right. That idea of how much you go down when you go to the right, how much the demand for a product decreases when you increase its price, is referred to the elasticity of the demand. We like to put things into categories, so we'll kind of pretend that goods are either elastic or inelastic. Elastic goods are goods like product E here, where if you raise the price a little bit, the quantity plummets. Inelastic goods are goods like product I here. The idea here is you can change the price, but that's not going to change the demand very much. With elastic goods, a change in price leads to a large change in demand. With inelastic goods, a change in price doesn't change the demand very much. Examples of elastic goods that are commonly quoted by textbooks are things like granola bars, right? Like, I don't know, Cliff Bars, sure. They're fine. They're like these little sugary treats that I take when I go hiking. They're like $1 each. However, if I go to the store to buy my Cliff Bars and now they're $2 each or something, I'm not going to buy no Cliff Bars. Because there's 10 other types of granola bars that are probably more or less the same. Some sugary mix of like oats and nuts or something that I just get instead. Similarly, like generic clothing, if you're not super into name brands and you're trying to buy a hoodie, you go to the store and they have 2 different hoodies there that are more or less the same, you're probably just going to get the one that's cheaper. If a company's trying to sell you hoodies and they raise their price, they're going to sell a lot less because you'll just buy a different hoodie. There's substitutes readily available. These generally aren't things that you necessarily need to survive. And if you do need something similar, well, there's plenty of options for you. Goods that fit this criteria are elastic goods. I always had a hard time keeping straight which one was the elastic one and which one was the inelastic one. So what I try to do, this isn't from a textbook or anything, is think about how the word elastic kind of captures that behavior, where if you change the price, the quantity is going to change a whole lot. And the way I think about it is I think about elastic as something that's flexible, right? Like the band on my sweatpants are elastic. So in the case of elastic goods, I think about the consumer as being super flexible. I don't need to buy a Cliff Bar. I can buy a, I don't know, Power Bar or something instead. I'm flexible. Whatever granola bar is cheapest is totally fine. I'm flexible like elastic. These are elastic goods. Goods that generally people think of as inelastic are things that you kind of have to buy no matter what. Utilities is a good example there. It's absurd how much I pay for internet at my house. I hate you, Comcast. I signed up, it was like $30 a month. Now it's like $75 a month or something just for internet. But I sure haven't canceled my internet because I kind of need internet. I work from home a lot. The same with things like prescription medicine. A big topic in the news is the ridiculous price of insulin. Costs like $0.25 to make it and then they charge it for like $100 or something. Good old American healthcare. But the reason they do that is because things like insulin are inelastic goods. People need it to survive. Raise the prices, people still got to buy it. So from the perspective of a corporation just trying to make money, since raising the price isn't going to change the quantity demanded a whole lot, they might as well raise the price. Anyways, ignoring any moral objections that you might have to raising the price of things that consumers absolutely need, hopefully you can see why we need a measure of how elastic a good is. If something is really elastic, you better not go raising the price because no one's going to want it anymore. But if something is relatively inelastic, well, then you might be able to make more revenue by raising your price. Well, there is a formula for such a thing. It's called the elasticity of demand, and it's given by this formula right here. A comment about this formula. So far, whenever I've talked about elastic and inelastic, I've just referred to goods. For example, I listed gasoline as inelastic. Go ahead and raise the price, it doesn't matter. People still need to fill up the tank to get to work. Raising the price of gas has a minimal impact on how much gas people demand. But that's a bit of an oversimplification. Demand curves are not linear like you see pictured here. Typically, demand curves are, well, curved. Here's a more realistic demand curve for something like gasoline. And I don't know exactly where the dollar amounts would be, but maybe I'll say this is $1 per gallon, 2, 3, 4, 5, and so on. When gas is pretty inexpensive, when gas is like, I don't know, $2 a gallon, increasing the price doesn't decrease the quantity a whole lot. Right? If I charge a little bit more, people still going to buy a lot of gas. But there is some point over here where if gas is crazy expensive, if gas is like, I don't know, $12.50 a gallon, people kind of reach their breaking point. They literally can't afford to fill their cars up. This is the point where people are like, all right, I guess I'm not going to drive to work anymore. I'm going to, I don't know, carpool or take the bus or ride my bike or whatever. At this point over here, if you increase the price even more, there's going to be a pretty substantial drop in the quantity that's demanded. Loosely speaking, my curve is a lot flatter here and a lot steeper here. So while it's easier to talk about goods as being either elastic or inelastic, that's a lie. Goods at a given price might be inelastic and at a different price might be elastic. And that's what this formula captures. Elasticity is not just a function of the good that we're talking about, it's also a function of price. So what this formula tells you is, if you increase the price by 1%, then your demand is going to decrease. How much is it going to decrease by? E%. So if E is less than 1, the idea is you're increasing your prices by a little bit, but E is really, really small. The demand is not going to decrease by very much. People still got to buy the gas. We would say the good is inelastic at that price. Think either product I over here in red, or gas when gas is relatively affordable. Contrast that with the case where E is greater than 1, where you change your price by a little bit and the demand decreases substantially, by a lot, a big number, more than 1. In that case, your good is elastic at that price. Think either product E or gasoline when people kind of reach their breaking point and they can't afford to fill up their tanks anymore. Generally speaking, if we're just trying to maximize revenue, if the elasticity of demand is less than 1, in other words, the good is inelastic at that price, we should raise the price. That's this case that's pictured in red right here. If people are still going to buy almost the same amount, you might as well charge them more for it. And if E is greater than 1, we would say the good is elastic at that price, and we should not raise the price. In fact, we should decrease the price. Wait, what? Yeah, that's this case over here in blue. You definitely don't want to raise the price because your demand will plummet. And so far, we've only been thinking about raising prices, but look what happens when you lower the price by a little bit. If you lower the price in blue by a little bit, quantity is going to skyrocket. Instead of selling 10,000 units for $50 each, maybe I could sell like 15,000 units for $40 each. Maybe that would allow me to make a lot more money. For our oversimplification purposes, if E is less than 1, we're going to call that good inelastic at that price, and we're going to raise the price if we want to raise revenue. If E is greater than 1, we're going to call that good elastic at that price, and decreasing the price will raise revenue. And finally, if E is equal to 1, neither less than or greater than 1, we're going to call that good unitary at that price. Think like unit, number 1. And in the language of previous sections, will be at a price that represents a critical value, a local maximum for revenue. That's a lot of talking. Maybe I can squeeze in one quick example to try to tie this together. Then we'll call this video good. In the previous section, I told you to consider some hypothetical good where if you charge $10, you're able to sell 200 units. But if you charge $20, then you're only able to sell 120 units. I told you to make the typically unrealistic assumption that the demand was linear. And what we did is we maximized revenue. Let's redo that example, but tie in the concepts that we've just learned about elasticity of demand. If we're going to learn anything about elasticity of demand, we need to know the equation of this demand function. Remember, we got the Q on the y-axis and the P on the x-axis, and we want to be able to write Q as a function of P. Well, because we have 2 points and this is assumed to be linear, we can first figure out the slope. Generally for slope, you're thinking y2 minus y1 over x2 minus x1. Although in this case, the y's are q's and the x's are p's. So if we call these points the 1s and these points the 2s, Q2 is 120 and Q1 is 200. P2 is 20 and P1 is 10. As we saw before, the slope of this curve is negative 80 divided by 10. In other words, negative 8. Now that we know the slope, we can use point slope form to come up with an equation that relates together the p's and the q's. For point slope form, you're thinking y minus y1 equals m times x minus x1. But again, the y's are q's and the x's are p's. So we got q minus q1 equals m times p minus p1. I'm just switching arbitrarily between lowercase and capital letters. Sorry about that. Anyways, plugging in values, I got q minus q1 we said was 200 equals m, which we calculated to be negative 8, times p minus p1, which we said was 10. We can solve this equation for q by maybe getting rid of the parentheses first. Q minus 200 equals negative 8p plus 80. And then adding 200 to both sides of the equation. Q equals negative 8p plus 280. If we want to write this in function notation, we have q as a function of p. Q is equal to negative 8 times p plus 280. Now that we know q is a function of p, we can find the derivative of q as a function of p. The derivative of this function is pretty easy to take. To take the derivative of a sum, we take the sum of the derivatives. The derivative of negative 8p is just negative 8, and the derivative of 280 is 0. So q prime of p is equal to negative 8. Now we want to find E of p, the elasticity of demand. Well, fortunately, we have this formula up here, and it says the elasticity at a given price p is equal to negative q prime of p times p over q. I'll copy it down here so I don't have to keep writing it. We have an expression for q prime of p. It's equal to negative 8. So we have the negative of negative 8 times p over q. P is a variable. We'll leave it as the letter p. And q is a function that we have an expression for in terms of p. Negative 8p plus 280. If I simplify this a little bit, I get my elasticity of demand at a price p is equal to the negative of negative 8, in other words, positive 8, times p divided by negative 8p plus 280. What can we do with this? Well, the original question was to find the elasticity of demand when the price is $10. So we're not trying to figure out E of p, we're trying to figure out E of 10. Well, that's easy enough. E of p is given by this formula, so E of 10 would be 8 times 10 divided by negative 8 times 10 plus 280. E of 10 is 80 divided by negative 80 plus 280, which is 200. If I reduce this fraction, I got 8 over 20, in other words, 4 over 10, in other words, 0.4. My elasticity of demand for this product when the price is $10 is 0.4. What does that mean? What's my conclusion? Well, note that 0.4 is less than 1. So we would call our good inelastic at that price, meaning we should raise the price to raise revenue. What should we raise the price to? Well, this doesn't immediately tell us what it is. It just says that there's some price that's more than $10 that would make us more revenue. And we can see that pretty easily, right? Revenue is price times quantity. At our current price of $10, our revenue is 10 times 200, in other words, $2,000. But if we raise the price all the way to $20, for example, then our revenue would be 20 times 120, which is $2,400, more than $2,000. I'm not saying that $20 is the optimal price. I'm just saying that if we raise the price to $20, we'd increase revenue. We're not charging enough because our good is inelastic at $10, something that we can figure out by calculating this elasticity of demand.